Right now, as you read these words, you are traveling through space at 828,000 kilometers per hour. You're spinning on a planet that's orbiting a star, which itself is racing around the center of a galaxy containing 400 billion suns. And that galaxy? It's hurtling toward a collision that will reshape everything we know about our cosmic home. But here's the truly mind-bending part. Every atom in your body was forged inside a dying star billions of years ago. You aren't just observing the universe. You are the universe awakened and looking back at itself. The iron in your blood once lived in the core of an exploding star. The calcium in your bones was born in a stellar furnace. The oxygen you're breathing right now, created in stars that died before our sun was even born. You are, quite literally, animated stardust, a way for the cosmos to know itself. Tonight, we're going to unravel one of the most spectacular stories ever told. How galaxies, those magnificent cities of stars, emerged from absolute darkness. We'll witness the birth of the first light after eons of cosmic silence. We'll watch galaxies collide in slow-motion ballet spanning billions of years. We'll discover invisible architects that hold the universe together, and we'll peek back in time to see the universe as it was when it was young, wild, and just learning how to shine. Before we begin, drop a comment below telling me where in the world you're watching from and what time it is. I'm always amazed by how many of us are exploring the cosmos together from different corners of our pale blue dot. Whether you're watching this in bright morning sunlight or the deep of night, know that you're part of a global community of cosmic explorers, all looking up and wondering about our place among the stars. So settle in, take a deep breath, let your shoulders drop, your jaw unclench, your thoughts slow down. You're about to journey through 13.8 billion years of cosmic history, and I promise you, by the end, you'll never look at the night sky the same way again. The stars won't just be distant points of light anymore. They'll be storytellers, historians, and long-lost relatives. They'll be home. Chapter 1, In the Beginning. When nothing became everything 13.8 billion years ago, there was no space, no time, no matter, no energy, not even darkness, because darkness implies space for darkness to exist in. There was quite literally nothing. And in a moment that defies comprehension, that nothing became everything. The Big Bang wasn't an explosion in space. It was the explosion of space itself. This is crucial to understand, and it's worth pausing on. There was no pre-existing void that suddenly got filled. Instead, every point in the universe expanded outward simultaneously, faster than light itself, like a balloon inflating at cosmic speed. But here's the kicker. There wasn't debris flying through empty space. Space itself was the debris, creating itself as it went, pulling time along for the ride. In those first fleeting microseconds, we're talking about time frames so small they make a blink of an eye seem like an eternity. The universe was unimaginably hot and dense. We're talking temperatures of around 1032 degrees Celsius. That's hotter than the core of any star you can imagine, hotter than anything we could ever hope to recreate in our most powerful particle accelerators. It was denser than anything we can comprehend, with all the matter and energy that would eventually become galaxies, stars, planets, and people compressed into a space smaller than an atom. It was a seething, roiling broth of fundamental particles, quarks jostling with gluons in a primordial soup, photons zipping around like restless children who've had too much cosmic sugar, and gravity, ever the patient sculptor, quietly taking notes on everything, planning its long game. This early universe was chaos incarnate. It was blindingly luminous, though there were no eyes to see it. It was screaming with energy, though there were no ears to hear. It was expanding faster than imagination, though there was no consciousness to marvel at it. This wasn't a place for stargazing or contemplation. Not yet. But this early universe, despite its violent chaos, was pregnant with infinite potential. Within the first 3 minutes, yes, just 3 minutes in the entire 13.8 billion year story, something remarkable happened. As the universe expanded and by cooled I mean dropped from unimaginable trillions of degrees to a mere billion or so, the simplest elements began to form. Protons and neutrons, which had been jostling around freely, started finding each other and sticking together. Hydrogen and helium nuclei snapped into being from the charged chaos like cosmic Lego bricks clicking into place. This process, called Big Bang nucleosynthesis, created the raw materials for everything to come. About 75% hydrogen, 25% helium, and trace amounts of lithium. These humble atoms would become the building blocks of everything. Stars, planets, moons, asteroids, comets, nebulae, people, pets, and yes, galaxies. Every breath you take contains hydrogen from this moment. Every star in the sky burns this primordial fuel. Fast forward 380,000 years. A cosmic blink, but still longer than all of recorded human history. The universe had cooled enough, down to about 3,000 degrees Celsius, still hot enough to vaporize any known material, but cool, by early universe standards, for something beautiful to happen. Electrons, which had been zipping around too fast to be captured, finally slowed down enough to be caught by atomic nuclei. Neutral atoms formed for the first time. This moment, called recombination, was transformative. Light, which had previously been trapped in the dense fog of charged particles, ricocheting around like a firefly, desperately seeking escape from a jar, was suddenly free to travel. The universe became transparent. The light released at that moment created what we now call the cosmic microwave background radiation, a soft afterglow that still permeates the universe today, detectable by our most sensitive instruments. If your eyes could see in microwaves instead of visible light, the entire sky would glow with the ancient fire of creation, a 13.8 billion-year-old baby picture of the cosmos. But here's the thing that would have frustrated any impatient cosmic observer. Despite this glow, despite this moment of clarity, there were no stars yet, no galaxies, no planets, no structures at all. Just a dark, expanding cloud of neutral gas, spreading outward into the growing fabric of space-time, filled with potential but utterly formless. Yet hidden within this apparent uniformity were subtle imperfections, ripples so faint they were barely there at all. Tiny irregularities in the otherwise smooth distribution of matter, density variations of less than 1 part in 100,000. Some regions were just slightly, infinitesimally, denser than others. The difference was barely measurable, hardly worth noticing, but gravity noticed. And gravity, as we'll see again and again, never forgets. These ripples were everything. They were the echoes of quantum fluctuations from the first fraction of a second after the Big Bang, stretched across the cosmos by the rapid inflation of space. They were the seeds from which all structure would grow. They were whispers that would become shouts, tiny wrinkles that would become the cosmic web, gentle perturbations that would blossom into galaxies containing hundreds of billions of stars. The stage was set, the ingredients were mixed. Now, the universe just needed time, lots and lots of time, to let gravity work its patient magic. Chapter 2. The cosmic ages silence before the symphony. After the brilliant opening act of the Big Bang and the soft glow of recombination, the universe went dark. Not empty, it was full of matter, swirling with hydrogen and helium gas, but lightless. We call this period the Cosmic Dark Ages. And despite the ominous name, which sounds like it should involve dragons and knights, it was simply an era of darkness in the purest sense. This cosmic intermission lasted for hundreds of millions of years, a pregnant pause in the universe's story. During this time, neutral hydrogen gas filled space like a vast invisible fog, thick and pervasive. No stars shone through it, no galaxies twinkled in the distance. No warm suns cast their glow on orbiting worlds. The universe was like a concert hall after the audience has left, and before the next performance of potential, full of equipment and staging, but eerily quiet and waiting. Imagine, if you can, floating through this time. You'd be surrounded by an infinite, expanding sea of cool hydrogen and helium gas, the temperature slowly dropping as the universe continued its relentless expansion. The occasional electron would drift by like a lazy jellyfish in a cosmic ocean. There would be gravity, yes, pulling ever so gently on the gas, forming invisible clouds here and there, nudging atoms closer together in some places than others. But everything would move at a glacial pace, imperceptible to any observer. Not that time meant much anyway. No clocks, no days, no sunrises to mark the passage of hours. Just the slow, patient accumulation of mass in a universe not yet in a hurry to become anything in particular. Yet, beneath this apparent stillness, something extraordinary was quietly unfolding. While the universe appeared dormant on the surface, invisible forces were hard at work. You see, during inflation, that lightning-fast expansion in the first fraction of a second after the Big Bang, tiny quantum fluctuations, smaller than atoms, were suddenly stretched across astronomical distances. These little wiggles in the fabric of space-time weren't much to look at, imperceptible really, but they created variations in density throughout the young universe. And over time, hundreds of millions of years, gravity took notice of these variations. Where matter was even a tiny bit denser, even by the smallest fraction of a percent, it began to exert slightly more gravitational pull. This pull attracted more matter, which increased the gravity, which attracted even more matter. It was a slow feedback loop, a cosmic snowball effect playing out over eons. These ripples grew into tendrils and knots, into a vast three-dimensional structure that we now call the cosmic web. Think of it like this. If you could see the universe from outside, from some impossible vantage point, it would look less like a uniform cloud and more like a vast sponge, or perhaps a three-dimensional spider web strung together by filaments of dark matter and gas, stretching across billions of light years. These filaments are where galaxies would eventually form, pulled into place by the persistent hand of gravity like beads, sliding along invisible strings. The empty spaces in between the voids would become giant, lonely stretches of near-nothingness, cosmic deserts where almost no stars would ever shine, where the silence would remain largely unbroken for the entire age of the universe. At the center of this architectural marvel was a silent partner, a mysterious substance we still don't fully understand. Dark matter. It doesn't glow or shine. It doesn't reflect light. It doesn't interact with electromagnetic radiation at all, which makes it famously difficult to study and, let's be honest, somewhat awkward at parties. You can't see it, can't touch it, can't detect it directly. But dark matter was absolutely essential to everything that followed. Its gravitational influence shaped the scaffolding of the cosmos, pulling ordinary matter, the hydrogen and helium gas that would eventually make stars, into place like the hidden frame beneath a magnificent painting. Dark matter created the gravitational wells, the invisible valleys and peaks in space-time, and ordinary matter flowed into them like water finding the lowest ground. Without dark matter providing this invisible framework, the tiny density variations from the early universe wouldn't have been enough. The hydrogen and helium gas would have remained too evenly distributed, too uniform. The universe might have stayed a foggy, formless cloud forever, expanding eternally without ever organizing itself into the spectacular structures we see today. Now, if you're still awake, and if you are, I truly admire your dedication to cosmic knowledge. You might be wondering, why did it take so long for the first stars to appear? If gravity was pulling gas together, why the hundreds of millions of years of darkness? Well, building a star isn't as simple as throwing gas into a blender and hitting the sun switch. It's a delicate process requiring specific conditions. Hydrogen had to fall into dense enough pockets for gravity to truly take over. As more gas accumulated in these pockets, the pressure at their centers began to increase. The gas had to be compressed enough that temperatures could rise to millions of degrees. Only then, at these extreme temperatures and pressures, could nuclear fusion begin. That nuclear dance where hydrogen nuclei overcome natural repulsion and fuse together to form helium, releasing tremendous amounts of energy in the process. This is what makes a star shine. But the early universe wasn't in a rush. It had all the time in the cosmos. It allowed gravity to work at its own methodical pace, slowly coaxing the gas into denser and denser clouds. Gradually, over hundreds of millions of years, these clouds collapsed under their own weight, each generation becoming more compact, more concentrated, more ready for what was coming. Somewhere in one of those especially dense knots of matter, pressure built to a critical point. Temperature soared. The center of the cloud became a crucible of unimaginable heat and pressure. And then, in a moment that changed everything, the first spark ignited. A single point of light appeared in an ocean of darkness. The first star was born. But here, during this long interlude of silence before that moment, the universe was still gathering its breath. Like an orchestra tuning before the conductor raises the baton, like actors taking their places before the curtain rises. The elements were in position, but the performance had yet to begin. No galaxies yet, no stars yet. Just a growing tension, a sense that something beautiful, something transformative was about to happen. The darkness was temporary, the silence wouldn't last forever. And perhaps that's the most comforting thing about this period in cosmic history. Even in the deepest darkness, even in the longest silence, the universe was never truly still. Beneath the surface, beneath the apparent emptiness, it was dreaming, organizing, preparing, structure was forming, potential was accumulating, the light was coming. And when it arrived, it would change everything. Chapter 3. Let There Be Light, the universe's first dawn somewhere, deep in a collapsing cloud of primordial gas, hydrogen and helium untouched by any previous generation of stars. Gravity finally tightened its grip to the breaking point. For hundreds of millions of years, this pocket of gas had been slowly contracting, drawn inward by its own mass, becoming denser with each passing millennium. At the cloud's center, atoms were being pushed closer and closer together, squeezed by the relentless pressure of all the matter pressing down from above. The temperature began to climb. First thousands of degrees, then tens of thousands, then hundreds of thousands. The atoms at the core were moving faster and faster, their thermal energy increasing, colliding with ever-increasing violence. And then, at around 10 million degrees Celsius, something magical happened. The hydrogen nuclei were moving so fast, carrying so much kinetic energy, that when they collided, they could overcome the electromagnetic force that normally keeps positively charged particles apart. They began to fuse, combining to form helium and releasing tremendous amounts of energy in the process. And in that moment, probably unnoticed by anything in the universe, certainly unceremonious in its execution, a star was born, the first light since the Big Bang, the end of the Dark Ages. A new chapter in the cosmic story, written in starlight and nuclear fire. These weren't ordinary stars, not by any stretch of imagination or comparison to what we see today. Known as population 3 stars, astronomers count generations backwards, somewhat confusingly. They were monsters, cosmic behemoths, unlike anything we can observe in the modern universe. They were enormous, unstable, and incredibly hot, glowing with an intense blue-white fury that would make our sun look dim by comparison. Some may have been hundreds of times more massive than our sun, perhaps even reaching 1,000 solar masses concentrated in a single burning sphere. To put that in perspective, if our sun were the size of a beach ball, some of these first stars would be as large as a small building. Their surface temperatures soared to 100,000 degrees Kelvin or more, making them shine with a brilliant blue-white light that could ionize gas clouds hundreds of light years away. They formed in the purest conditions the universe has ever known or will ever know again. There were no heavy elements contaminating the pristine mix, no carbon to alter the chemistry, no oxygen to complicate the fusion reactions, no iron lurking in the gas to poison the nuclear processes. Just hydrogen, about 75 pure, helium, about 25, and trace amounts of lithium, a few parts per billion, all remnants from the Big Bang itself, untouched by stellar processing. This pristine composition had profound consequences. It meant these stars burned hotter and faster than any stars in the modern universe. They were like cosmic Roman candles, blazing brilliantly but briefly, living lives measured in millions of years, rather than the billions of years that smaller, metal-enriched stars can enjoy. They were beautiful disasters, magnificent catastrophes, essential to everything that followed but doomed from the moment of their birth. Their lifespans were tragically short, perhaps only a few million years for the most massive examples, maybe tens of millions for the smaller ones. Compare that to our sun, a thoroughly average star, which will shine steadily for about 10 billion years total. These first stars lived fast and died young, ending their brief but spectacular lives either by collapsing directly into black holes or exploding in brilliant supernovae that would have been visible had there been eyes to see them, telescopes to detect them, halfway across the observable universe. If you were somehow floating nearby one of these stellar giants. Though, let's be absolutely honest, you'd be instantly vaporized, your atoms torn apart and ionized before you could even register what was happening. You'd witness something breathtaking. These first stars were lighting up their surroundings like cosmic bonfires in a vast, dark forest that had never known flame. Their intense ultraviolet and X-ray radiation flooded outward in all directions like a tidal wave of energy. And as this radiation encountered the neutral hydrogen fog that still filled most of the universe, something remarkable began to happen. The ultraviolet photons carried enough energy to strip electrons from hydrogen atoms, ionizing them once again and reversing the recombination that had occurred hundreds of millions of years earlier. This process, which astronomers call cosmic reionization, and which sounds like something a supervillain might attempt with a doomsday weapon in a science fiction novel, gradually cleared the fog that had shrouded the universe throughout the Dark Ages. It was peaceful in its mechanism, albeit dramatic in its effects, like watching the sun burn through morning mist, revealing the landscape beyond, transforming obscurity into clarity. One by one, star after star ignited across the cosmos, each one separated by millions or tens of millions of light years, but collectively transforming the universe. Each new star carved out a bubble of ionized gas in its surrounding region, a sphere of transparency in the fog. These bubbles grew outward at nearly the speed of light, expanding as the star's radiation traveled further and further from its source. Eventually, these bubbles merged with neighboring bubbles created by other young stars, Slowly, over perhaps 100 million years or more, the universe transitioned from being predominantly neutral and opaque to being mostly ionized and transparent once again. It was as though someone had systematically cracked open the shutters of a cosmic greenhouse, one window at a time, until the entire structure was flooded with light and clarity, transforming the view both inside and out. From our perspective today, billions of years later and billions of light years away, standing on a small rocky planet orbiting an ordinary yellow star in an unremarkable spiral galaxy, we face a frustrating reality. We can't see these first stars directly. They were too brief in their lifespans, too distant in space and time, and by the time their light would theoretically reach us, they'd already been dead and gone for billions of years. Their light has been stretched and redshifted by the expansion of the universe to the point where it's nearly impossible to detect above the background noise of space. But their fingerprints, their legacy, their influence, these are everywhere we look. They fundamentally transformed the universe from cold and dark to warm and glowing. They seeded the cosmos with the first heavy elements ever to exist, the building blocks of everything more complicated than hydrogen and helium. Every carbon atom in your DNA, every oxygen molecule you breathe, every calcium ion strengthening your bones, every iron atom in your blood can ultimately trace its lineage back to stars like these, or to their countless descendants. In a very real and profound way, these stars were the universe's first artists, sketching the outlines of structure on the blank canvas of space, preparing the cosmic gallery for all the masterpieces that would follow. They were pioneers, venturing into territory where nothing had ventured before, making it safe and fertile for everything that came after. But galaxies still hadn't formed. Not quite. Not yet. These early stars were often scattered in small clusters or loose groups, bound together by their mutual gravity, but not yet organized into the grand swirling cities of stars. The majestic spiral and elliptical structures we see through modern telescopes. These primitive groupings were more like cosmic villages or perhaps proto-galaxies, drafts, experiments, the universe testing the waters of large-scale structure and stellar cohesion before committing to anything permanent or elaborate. Yet even in this primitive, scattered state, the crucial ingredients were coming together. The recipe was being refined. As these massive first-generation stars ended their short lives in violent supernovae explosions, they acted as cosmic foundries and alchemical laboratories. In the incredible heat and pressure of their collapsing cores and exploding outer layers, they forged elements heavier than helium. Carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, calcium, iron, and dozens of others, creating the entire middle section of the periodic table in mere seconds of explosive fury. These supernova explosions blasted these newly created heavy elements outward into the surrounding gas clouds at speeds of thousands of kilometers per second, enriching the pristine hydrogen-helium mixture, changing its fundamental chemistry, giving it new properties and capabilities. This enrichment was crucial, a game changer in cosmic evolution. You see, gas clouds with even trace amounts of heavy elements, what astronomers call metals, even though that's not quite accurate by chemistry standards, could cool more efficiently than the pure hydrogen-helium mixture of the early universe. These heavier atoms and molecules could radiate away thermal energy more effectively through various emission processes. This meant enriched clouds could lose their heat faster, collapse more quickly under their own gravity, and form stars with greater ease and at lower masses than was possible for the first generation. The next generation of stars, what astronomers call population 2 stars, began to appear across the cosmos. They were a bit smaller than their predecessors, ranging from perhaps 10 to 100 solar masses rather than hundreds or thousands. They were a bit more stable, with lifetimes measured in tens or hundreds of millions of years. And they already felt more familiar, more like the stars we know and study today, more like distant cousins to our own sun. And thus, the great cosmic cycle began its endless spinning, a wheel of stellar birth and death that would turn for billions of years and continues turning even today. Gravity pulls in gas from the surrounding space. Stars are born from the accumulation and compression of this material. They shine for their allotted time, fusing lighter elements into heavier ones in their nuclear furnaces. Eventually, they die either quietly, if small, or violently, if large, scattering their enriched contents back into the interstellar medium. This enriched material mixes with fresh hydrogen and joins new clouds of gas, allowing even more stars to form, each generation more chemically complex than the last. Each generation builds upon the ashes of the last, layering complexity like cosmic sediment, like archaeological strata in the soil of the universe, like pages being added to a history book one chapter at a time. The universe was no longer a blank slate, a tabula rasa. It was beginning to write its own story, one star at a time, one supernova at a time, one enriched gas cloud at a time, building towards something grander, more structured, more alive than anything that had come before. The darkness had ended, light had returned to the cosmos, and the age of galaxies was about to begin. Chapter 4. The first galaxies take shape. From villages to cities, the stars had arrived, piercing the darkness with their light, but they were scattered across the cosmos, isolated points of brilliance, flickering across the void like distant campfires on a dark plain. There were no cities yet, no roads connecting these lonely outposts of light. The universe was still fragmented, still finding its way toward organization. But gravity, patient and persistent as always, had other plans. Those scattered stars weren't floating randomly through space like cosmic dandelion seeds blown on an intergalactic wind. No, they were being drawn together by invisible threads of gravitational attraction, pulled along the filaments of dark matter that stretched across the universe like a cosmic neural network. Small clumps of dozens or hundreds of stars began converging, merging, growing. Gravity was quietly but inexorably threading them into larger, more complex structures, building cosmic communities one star at a time. The transformation was gradual but profound. Villages of stars became towns, towns became cities, and these chaotic, early, rough around the edges stellar metropolises were the first drafts of what we now call galaxies. They were the prototypes, the beta versions, the works in progress that would eventually evolve into the magnificent structures we observe through our telescopes today. It didn't happen neatly or according to any plan. There were no blueprints, no cosmic engineers with rulers and compasses marking out spiral arms and central bulges. There was no intelligent design, no guiding hand. Instead, there was chaos, beautiful, productive, creative chaos. It was messy, uncontrolled, and often violent. Clumps of stars collided and merged. They ripped each other apart through tidal forces, only to merge again in new configurations. Stars were flung from one group into another, like cosmic refugees seeking new homes. Gas clouds crashed into each other with tremendous force, compressing violently and sparking new explosions of star formation. The early universe was a rough neighborhood, cosmologically speaking. If galaxies could have insurance policies, the premiums would have been astronomical. Everywhere you looked, had there been anyone to look. Proto-galaxies were interacting, colliding, merging, splitting, and generally causing mayhem across the cosmic landscape. Some early galaxies formed quickly, growing fat on nearby reservoirs of gas and greedily gobbling up their smaller neighbors in acts of cosmic cannibalism. Others stalled in their development, stranded in quiet corners of space where gas was scarce, like wallflowers at the universe's biggest dance party, waiting for a partner who would never arrive. At this early stage, somewhere between 500 million and 1 billion years after the Big Bang, galaxies didn't look anything like the elegant spirals or massive ellipticals we see in glossy telescope images and astronomy textbooks. They were irregular, chaotic, unrefined, asymmetrical, more like cosmic blobs or abstract sculptures than the symmetrical beauties you might picture when someone says galaxy. They were works in progress, sketches rather than finished paintings. And yet, even in their chaos, even in their irregularity, they were growing, maturing, slowly finding their form. Their shapes began to stabilize, nudged by the relentless laws of gravity, and sculpted by their local environments, by the amount of gas available, by the frequency of collisions with neighbors, by the strength of the dark matter halos that surrounded them. Much of this early architectural development was influenced by structure on an even larger scale. The cosmic web we discussed earlier, this vast three-dimensional lacework of matter, woven across the universe like an intricate tapestry, determined where galaxies would flourish and where they would struggle. Dense knots where multiple filaments of dark matter intersected became the hubs, the downtown districts of the cosmos, regions where galaxies would cluster together like seeds finding the richest soil, like settlers building towns at the crossroads of major trade routes. Long tendrils of matter stretched between these intersection points, pulling galaxies along invisible rails of gravitational potential. And in between these glowing threads, vast voids spread, eerie and silent regions, cosmic wastelands where few galaxies would ever form, where the silence and darkness would persist largely uninterrupted for the entire age of the universe. It was in these dense intersections, these cosmic crossroads, that proto-galaxies had the most to gain, and paradoxically, the most to fear. When you concentrate a lot of gas and gravity in one place, when you pack young galaxies close together, things tend to get dramatic. Interactions become frequent. Collisions become inevitable. Galaxies would crash into one another in slow-motion dances that could take hundreds of millions of years to complete from first contact to final merger. These weren't violent collisions in the way you might expect from watching science fiction movies. Stars themselves are so incredibly far apart, even within galaxies, that most didn't hit anything at all during these mergers. A star colliding with another star was and remains vanishingly rare, like two specific raindrops colliding in a storm. But while the stars mostly passed by each other harmlessly, their gravitational fields did tangle and interact. Tidal forces, the same forces that cause Earth's ocean tides, twisted entire galaxies into strange, beautiful, sometimes grotesque shapes. Streams and ribbons of stars were pulled away from their home galaxies like taffy being stretched, trailing behind in long luminous tails that could span hundreds of thousands of light years. Gas clouds, unlike stars, did collide with spectacular results. When two clouds of hydrogen and helium gas slam into each other at velocities of hundreds of kilometers per second, they don't just bounce off. They compress violently, heating up, increasing in density, and where you have dense, hot gas, you get star formation. Lots of star formation. This compression triggered what astronomers romantically call starbursts, dramatic explosions of stellar birth, where hundreds or even thousands of stars could form in regions just a few hundred light years across. These starburst events could create more stars in a few million years than a galaxy might normally produce in a billion years of peaceful evolution. It was like going from a gentle rain to a monsoon, from a trickle to a flood. So amid all the chaos, amid all the collisions and near misses and gravitational wrestling matches, new stars bloomed in abundance. New stellar clusters formed, each one a concentrated ball of hundreds or thousands of stars born from the same cloud of gas. And over time, tens or hundreds of millions of years, what was once a shapeless, irregular clump of stars and gas began to resemble something more familiar, something more organized, something that deserved to be called a galaxy. Those scattered stars weren't floating randomly. Invisible threads of dark matter were drawing them together. Small clumps of stars converged, pulled by gravity into larger structures. Villages became towns, towns became cities, and these cities, these proto-galaxies, were the first drafts of what we now call galaxies. It didn't happen neatly. There were no blueprints, no cosmic architects with rulers marking out spiral arms. It was messy, chaotic, beautiful in its disorder. Clumps collided and merged. Stars were flung from one group to another like cosmic refugees. Gas clouds crashed together, compressing violently and sparking new waves of star formation, what astronomers call starbursts. Early galaxies didn't look like the elegant spirals we see in glossy photographs. They were irregular, unrefined, more like cosmic blobs than symmetrical beauties. But they were growing, and slowly their shapes began to stabilize. The cosmic web played a crucial role in this architecture, where filaments of dark matter intersected, galaxies clustered like seeds finding the richest soil. These dense intersections became hubs of activity and drama. When you have lots of gas and gravity in one place, collisions become inevitable. Galaxies crashed into one another in slow-motion dances that took hundreds of millions of years. Stars themselves rarely collided. They're too far apart. But gravitational fields tangled together. Tidal forces twisted galaxies into strange shapes. Streams of stars were pulled like cosmic taffy. Yet amid the chaos, new stars bloomed, and over time, shapeless clumps began to resemble something more familiar. What determined a galaxy's final form? Galaxies that stayed relatively undisturbed, with just the right amount of spin, could flatten into elegant spirals. Others, buffeted by collisions or formed in crowded environments, became ellipticals, round, puffy collections of older stars. Some never settled down at all, remaining forever lopsided. We call these irregular galaxies, and frankly, we love them for their chaotic energy. But regardless of shape, galaxies had become something new, star forges, where gravity and gas came together to ignite creation. Chapter 5. The architecture of galaxies. By now, galaxies had found their forms, and the diversity is stunning. Let's explore the three main types. Asterisk spiral galaxies are the show-offs, the ones on posters and desktop wallpapers. With graceful curving arms and luminous cores, they look like cosmic hurricanes frozen in time. Our Milky Way is a spiral galaxy, and we live tucked into one of its arms like suburban residents on the edge of a great rotating city. Spirals form when a galaxy has moderate angular momentum, when gas and stars rotate in an orderly fashion, naturally flattening into a disk. Density waves ripple through that disk, compressing gas and sparking star formation. The result? Spiral arms that aren't rigid structures, but patterns moving through the galaxy like traffic jams in space. Stars move in and out of them, but the arms persist, lit up by bright young stars like festive lights. Asterisk elliptical galaxies are older, rounder, more relaxed. They lack spiral arms, appearing instead as giant star clouds shaped like spheres or rugby balls. They're usually composed of older, redder stars, with little gas left for making new ones. If spirals are bustling cities, ellipticals are sleepy retirement communities. Quiet, stable, not big on change. Ellipticals typically form through galactic mergers. When two spirals crash together, their orderly motion is disrupted. Stars are flung into random orbits. Gas gets used up or blown away. What remains settles into a shapeless mass, dramatic and oddly productive, like smashing two snow globes together and letting the flakes resettle. Asterisk irregular galaxies are the oddballs, the nonconformists. Some are young galaxies that haven't had time to form a shape. Others are older ones pulled out of alignment by close encounters with larger neighbors. They might look like splatters or scribbles, but they're often bursting with new stars, full of energy and potential. Galaxy shape isn't just aesthetic, it tells us about history. A spiral likely had a calmer upbringing. An elliptical probably saw battle. And irregulars? They might just be young, unlucky, or both. Chapter 6. Coming home to the Milky Way. Our cosmic address. Let's return to our corner of the cosmos, to the one place that we can truly call home. We live inside a galaxy called the Milky Way, and from our place within it, embedded in one of her spiral arms, we can't actually see it as a whole. It's like trying to read a label from inside the bottle, or appreciating a cathedral's architecture while standing inside one of its walls. What we do see on clear dark nights far from light pollution is something equally spectacular, a glowing river of light stretched across the night sky like a luminous highway. A shimmering band that ancient cultures named after spilled milk, pathways to the gods, celestial rivers. That shimmering band, part dust, part starlight, part nebulae, is our view across the galactic plane, looking edge-on through billions of stars. The Milky Way is a spiral galaxy, one of billions in the universe, and quite a large one at that. She stretches about 100,000 light-years from edge to edge, a distance so vast that light takes 100,000 years to cross from one side to the other. To put that in perspective, the light we see from the far side of our galaxy left before modern humans fully evolved, before the last ice age, before we developed language or art. The galaxy contains somewhere between 100 and 400 billion stars. Yes, that's quite a range. Why can't we count more precisely? It's extraordinarily hard when you're stuck inside the middle of them, looking through thick clouds of obscuring dust. It's like trying to count all the trees in a forest while standing in it during a foggy night with only a flashlight. But the best estimates place us roughly 1/3 of the way from the center, residing in a minor spiral arm called the Orion Arm. Cosmic suburbanites living between downtown and the rural outskirts, not too close to the chaos, not too far from the action, in a comfortable middle ground perfect for the evolution of life. The center of the Milky Way is busy, energetic, crowded. It houses a supermassive black hole with the designation Sagittarius A, pronounced Sagittarius A star, a gravitational heavyweight roughly 4 million times the mass of our sun. 4 million suns' worth of matter compressed into a region smaller than Mercury's orbit. It's not the brightest object. Black holes don't emit light by definition, and it's not particularly active by cosmic standards. But it anchors the entire galaxy through its immense gravitational influence. Stars whirl around Sagittarius A in dizzying orbits, some completing circuits in as little as 16 years, racing at speeds up to 5,000 kilometers per second, more than 1% the speed of light, like moths circling an invisible flame. We know this black hole exists not because we can see it. We can't. It's black, and there's dust in the way, but because of how it affects its surroundings. Imagine watching stars move as if caught in an invisible whirlpool, orbiting around apparently empty space. Astronomers have tracked individual stars near the galactic center for decades, plotting their positions year after year. The evidence is overwhelming. Something incredibly massive, compact, and dark sits at the galactic center. And no, it's not planning to eat Earth anytime soon. We're far too safely tucked away in our suburban spiral arm. The Milky Way didn't always look this way. Like all galaxies, it has a long, occasionally turbulent past. It formed over billions of years through mergers and acquisitions. Smaller galaxies were pulled in, digested, folded into the spiral. Stars from these devoured galaxies still linger in the Milky Way's outer halo, orbiting on long looping paths like wandering ghosts from long-lost homes. And it's still happening now. Even as you read this, the Milky Way is pulling apart several smaller galaxies. The Sagittarius dwarf galaxy is being slowly unraveled and absorbed. Not violently, not on human timescales, but over millions of years, like watching a drop of ink slowly swirl into water. Even more dramatically, we're on a slow-motion collision course with Andromeda, our nearest large neighbor, currently about 2.5 million light-years away, but heading straight for us at roughly 110 kilometers per second. Don't worry, you have about 4 billion years to prepare. When it happens, it won't be the end. The two galaxies will merge into a new one, possibly an elliptical galaxy. Astronomers have suggested the name Milky Way, which sounds like space yogurt, but we'll let it slide. What's astonishing is that we can tell all this from inside the galaxy. Thanks to radio telescopes, infrared observations, and clever mathematics, we've mapped the spiral arms, traced star populations, and simulated the galaxy's formation and fate. It's like piecing together a jigsaw puzzle from the inside. Our sun takes about 225 million years to make one complete lap around the galactic center. We've only made about 20 trips since the sun formed. The last time we were in this neighborhood, dinosaurs were just beginning to roam Earth. Galactic years aren't measured in birthdays, but in epochs. Here we are, spinning quietly in a spiral arm, a pale blue dot circling an unremarkable yellow star, wrapped in the soft light of a billion suns. Every atom in your body was forged in stars that lived and died long ago, possibly in galaxies later folded into our own. You are literally part of the Milky Way's story, a moving, breathing fragment of galactic history, animated stardust listening to starlight. The galaxy isn't just out there, you carry it within you. The Milky Way didn't always look this way. Like all galaxies, it has a turbulent past, formed through mergers and acquisitions. Smaller galaxies were pulled in, digested, and absorbed. Stars from these devoured galaxies still orbit in the Milky Way's outer halo like wandering ghosts from lost homes. This is still happening. Right now, the Milky Way is pulling apart several smaller galaxies, including the Sagittarius dwarf galaxy, slowly unraveling and absorbing it like watching ink swirl into water. Even more dramatically, we're on a collision course with Andromeda, our nearest large neighbor, currently 2.5 million light-years away, but approaching at 110 kilometers per second. Don't worry, you have about 4 billion years to prepare. When it happens, the two galaxies will merge into a new one, possibly an elliptical galaxy astronomers have nicknamed Milky Way, which sounds like space yogurt, but we'll let it slide. Our sun takes about 225 million years to make one complete orbit around the galactic center. We've only completed about 20 laps since the sun formed. The last time we were in this neighborhood, dinosaurs were just beginning to roam Earth. Galactic years aren't measured in birthdays, but in epochs. Here we are, spinning quietly in a spiral arm, a pale blue dot circling an unremarkable yellow star, wrapped in the soft light of a billion suns. Every atom in your body was forged in stars that lived and died long ago, possibly in galaxies later folded into our own. You are literally part of the Milky Way's story, a moving, breathing fragment of galactic history. Chapter 7. The Invisible Architects. If galaxies are the great cities of the cosmos, what built them? Three unlikely architects have been quietly at work since the beginning. Gravity, dark matter, and black holes. Asterisk, gravity is the great gatherer. It doesn't make a fuss. It simply pulls. Always has, always will. In the early universe, gravity took those tiny density ripples and amplified them, drawing gas and matter together until stars and galaxies could form. It's slow, patient, and never stops working. Here's the thing. Gravity is actually the weakest of the four fundamental forces. Drop a paperclip and gravity pulls it down. Hold a magnet above it, and suddenly the paperclip defies an entire planet's gravitational pull. But gravity shapes the cosmos. Because it accumulates, it never cancels itself out. The more mass you have, the more gravity you get. In the vastness of space, gravity's quiet persistence adds up. Asterisk, dark matter is the mysterious substance we cannot see, touch, or smell, yet we're almost certain exists because its gravitational fingerprints are everywhere. When astronomers measured how fast stars orbit in galaxies, they found something strange. Outer stars were moving far too fast. They should have been flung off into space like glitter from a spinning wheel, but they weren't. They stayed put, stable, loyal. This was a problem, unless there was more mass than we could see. A lot more. Dark matter doesn't interact with light. It doesn't glow, but it exerts gravity. And there's about 5 times more dark matter than normal matter. Every visible star or gas cloud in a galaxy sits within a much larger invisible halo of dark matter, holding everything together. Without it, galaxies couldn't exist. No one knows exactly what dark matter is. There are theories, exotic particles, supersymmetric partners, ideas involving extra dimensions, but none confirmed. Still, its effects are undeniable. Like wind on the ocean, we don't need to see it to know it's there. Asterisked, supermassive black holes sit at the centers of nearly every large galaxy, including our own. They range from millions to billions of times the sun's mass. While they have a reputation for destruction, they're more like galactic administrators, quiet, mysterious, and extremely influential. We used to think black holes were just passengers, but we've realized they're co-authors of a galaxy's story. When they feed on gas and dust, they release enormous energy, often more than all the galaxy's stars combined. This energy can blow away gas needed for star formation, halting it for millions of years. Black holes don't just sit there. They regulate growth and shape galactic fate. It's ironic. The darkest things in the universe are also what holds it all together. Dark matter, gravity, black holes, the unsung architects of everything. The beauty you see in the night sky is only half the story. The rest, the invisible scaffolding, the silent forces, is still there, not shining or speaking, but building, always building. Chapter 8. When galaxies collide, galaxies may look serene in photographs, but the universe is not quiet. Galaxies are constantly moving, drifting, orbiting, pulled by gravity like dancers in an endless waltz. And occasionally, those dancers get too close. Yes, galaxies crash into each other. But before you imagine stars exploding like marbles, take a breath. The reality is more poetic. Despite their size, galaxies are mostly empty space. Even in a full-blown collision, the chance of 2 stars actually hitting each other is vanishingly small. It's like watching 2 fog banks pass through each other. Only the fog is made of stars, gas, dust, and dark matter. While stars avoid direct collisions, galaxies don't emerge unchanged. Their gravity pulls and stretches them, distorting shapes into long flowing tendrils called tidal tails that can span hundreds of thousands of light years. They look like glowing ribbons unraveling into space. Gas clouds, however, do collide with gusto. When they crash, they compress, heat, and often trigger dramatic bursts of star formation. These starburst galaxies can produce stars at rates dozens or hundreds of times faster than usual. A cosmic baby boom sparked by gravitational chaos. Some of the most beautiful galaxies we've observed are caught mid-collision. The antennae galaxies, for instance, 2 spirals merging, show long curling arms and brilliant regions of new star formation. Eventually, they'll settle into one, usually a large elliptical galaxy. Spiral structures are delicate and easily disrupted. After a major merger, orderly orbits randomize and gas is used up or flung away. This isn't ancient history. The Milky Way is currently merging with several small dwarf galaxies, and Andromeda is approaching. In 4 billion years, they'll collide in a spectacular slow-motion dance. What will happen to us? Surprisingly little. Stars are so far apart that direct collisions are unlikely. But the night sky will change. Over millions of years, Andromeda will grow larger and brighter, eventually dominating the view. These interactions aren't just destructive, they're creative. Mergers can restart star formation, feed black holes, and create entirely new structures. Like pruning a tree or mixing paint, the result is something new. Messy at first, but often more vibrant. To gaze into space is to gaze into time. Every star you see shows you not how it looks now, but how it looked then. Light, despite its speed, takes time to travel. The sun's light is 8 minutes old when it reaches us. Alpha Centauri's light is over 4 years old. Andromeda's glow? More than 2.5 million years old? That light began its journey before the first humans. But we can go even further. With telescopes, we peer back billions of years almost to the beginning. The deeper we look, the further back we go, peeling away layers of cosmic history one photon at a time. The asterisk Hubble Space Telescope, launched in 1990, showed us things we never imagined. One of its most famous achievements is the Hubble Deep Field. Astronomers pointed it at what seemed like a completely empty patch of sky and let it stare for days. When images came back, that nothing became a sea of thousands of galaxies, some over 13 billion years old, almost to the moment galaxies first formed. Now we have the asterisk James Webb Space Telescope, launched in 2021. Webb sees even deeper because it observes in infrared. As the universe expands, light from distant galaxies is stretched to longer wavelengths, called redshift. The earliest galaxies now shine mostly in infrared, which Webb was built to capture. Already, Webb is showing us galaxies from just a few 100 million years after the Big Bang. Some are small and chaotic as expected. Others are surprisingly mature, like finding fully grown cities right after the first huts were built. These discoveries are reshaping our understanding of galaxy formation. The farther away a galaxy is, the younger it appears because we see it as it was billions of years ago. We can't rewind the universe, but we don't need to. It has already sent its memories to us, one photon at a time. There's a limit to how far we can see. The cosmic microwave background, the afterglow of the Big Bang. Before that, the universe was opaque, light couldn't travel freely. That's our cosmic horizon. Every image from Webb, every frame from Hubble is a photograph of the past. A snapshot so distant, it feels like fiction, but it's real. That light touched something once and now touches you. Chapter 10. The modern universe. We've traveled far, from the first whispers of matter to sprawling spirals and glowing cores. Now, in the present, we find the universe still evolving. Galaxies continue forming, merging, reaching toward one another. Galaxies don't live alone. They gather into groups, clusters, and superclusters. Structures so vast they defy imagination. Our asterisk Milky Way is part of the asterisk local group made up of more than 50 galaxies, most small and faint. The two largest members are us and Andromeda, twin giants of this galactic suburb, slowly spiraling toward each other. Zoom out and you find galaxy asterisk clusters, collections of hundreds or thousands of galaxies bound by gravity. The Virgo cluster, for example, sits just beyond our local group, filled with spirals, ellipticals, and every shape in between. These clusters are embedded in even grander formations, asterisk superclusters. The Laniakea supercluster, our cosmic address, stretches over 500 million light-years and contains about 100,000 galaxies. That's 100,000 galaxies, each with billions of stars, all drifting together through the cosmos. And even that is just a thread in the asterisk cosmic web, the vast structure forming the skeleton of the universe. Galaxies aren't randomly sprinkled through space. They form patterns, filaments, sheets, and nodes like foam stretched across a dark sea. Between these filaments lie asterisk void men's empty regions where few galaxies exist, some tens of millions of light years wide, dark, and silent. Not everything is growing. Many galaxies, especially mature ellipticals, are no longer forming stars. They've used up their gas. We call them red and dead, not lifeless but aging, with no new stars replacing old ones. Even our Milky Way forms fewer stars than it once did. We're in a quieter, more reflective chapter. And the universe itself? It's expanding faster due to asterisk dark energy, a mysterious force pushing galaxies apart at accelerating speeds. Over trillions of years, galaxies not bound to us by gravity will vanish from view. Their light stretched until it can no longer reach us. The universe will grow colder, quieter, more isolated. But we've got time, a lot of time. For now, galaxies continue to evolve and surprise us. With telescopes peering deeper into space and further back in time, we're catching echoes of galactic birth, ripples of collisions, the faint glimmer of newborn stars in galaxies so distant their light left before Earth had oceans. Closing, you are stardust. An invitation to wonder after billions of years and billions of light years. After watching the universe transform from formless chaos into structured beauty, we've come to the end of our journey. We've drifted from the birth of the universe through the cosmic dark ages to first light. We've watched stars flare into life, cluster into cities of fire, and spin through spirals shaped by invisible hands. We've seen galaxies collide and merge in slow-motion ballets, fade and grow old, quiet giants in a living cosmos that never stands still. We've journeyed through the Milky Way, our own galactic home, a spiral city of hundreds of billions of stars where we occupy one small, comfortable corner. We felt the pull of black holes and dark matter, the quiet, invisible architects of all that we see. And we've looked back in time, really looked, catching ancient light that traveled across the entire universe just to meet us here now in this moment. It's humbling, isn't it? To know that the stars above are not just points of light, but memories frozen in the fabric of space-time. That galaxies are not still images in a cosmic photo album, but stories still unfolding, chapters still being written. That everything around you, your hands that turn pages or scroll screens, your breath that fills your lungs, the thoughts floating through your consciousness, was forged in the heart of a long-dead star that exploded billions of years ago. You are made of galaxy stuff, quite literally. The iron in your blood, the calcium in your bones, the carbon in your cells. All of it was created in stellar furnaces and scattered across space by supernova explosions. You are recycled stardust animated by the same forces that govern galaxies. You are part of the story, not separate from it. And maybe, just maybe, that's why we find the night sky so comforting, so mysteriously familiar. Why something inside us quiets and opens when we look up at stars. Because some ancient part of us, some cellular memory, remembers what it feels like to drift through starlight, to be part of the cosmic dance, to belong to something infinitely larger than ourselves. The universe doesn't just tell stories, it remembers them. It carries them forward through time, in the light of distant stars, in the spin of galaxies, in the atoms that make up our bodies. And now, through this journey we've taken together, you remember too. You carry this story now, this understanding of where we came from and how we got here. Before you go, before you close your eyes or move on to whatever comes next, drop a comment telling me where you're watching from and what time it is in your corner of the world. I love hearing how these cosmic journeys connect us across the globe, how people from different countries, different time zones, different walks of life can all share this sense of wonder about our universe. It reminds me how we're all connected, not just metaphorically, but literally, through the stardust we're made of, through the curiosity we share, through our common cosmic origin. If you enjoyed drifting through the cosmos with me tonight, consider leaving a like or subscribing for more explorations. There's a whole universe waiting for us, endless mysteries to ponder, endless beauty to appreciate, endless stories to tell. And I'd love to explore it all with you. But for now, rest. Let the stars keep their eternal watch. Let the galaxies continue their slow cosmic dance, spiraling through space just as they have for billions of years, and will for billions more. The universe is patient. It will still be here when you wake. Good night, fellow traveler. Sleep well, knowing you are home, home among the stars, home in a universe that made you from its own substance, home in the grandest story ever told. Welcome home.